Plants are going to use light energy, which saw earlier is a type of kinetic energy in order to do photosynthesis, so we need to talk about it a little bit. Light energy is going to be packaged into these little energy packets called photons. And these photons are going to travel, so that's why they're a type of kinetic energy, and they're going to be traveling in waves. So we're going to look at what we call the electromagnetic spectrum, if you've heard of that before. The electromagnetic spectrum basically just lays out all of the different types of energy that travel in waves. The visible light spectrum is part of that. You can see that we've got things like radio waves, infrared, which lots of different things run on this. So a lot of your electronics, like your remotes and things like that, run on infrared, but so does your microwave. So that's how it heats things up. UV, so that's the part of sunlight that can do damage to your skin and cells. X-rays, a pretty powerful version of the electromagnetic spectrum. The waves are traveling at fairly high energy with short wavelengths, so that's how they're able to penetrate our skin. And then gamma rays, these are, as you can see, radioactive. They can do quite a bit of damage. They are basically pure energy that are traveling at incredibly high energy levels. So what part are we concerned about? Like I said, these are a range of waves, and the shorter the wavelength, the higher the energy. Well, the part that we're concerned about is the visible spectrum, because this is the part not only that we can see in, but the part that plants use. And you can see even in the visible light spectrum, the shorter the wavelength, the higher the energy, because you've got the purple in this section, they are on the shorter wavelength end. They're going to have higher energy than the reds, which are on the lower wavelength. So the bigger the number, the longer the wavelength, and therefore the lower the energy. So that visible spectrum, like I said, this is the part that we can see as light, but what plants also use for photosynthesis. You may have heard the visible spectrum referred to as Roy G. Biv for the colors that are in the spectrum. So those are the main colors. Obviously, it's a spectrum, so it ranges against all of the different colors that are there. But, red, orange, yellow, green, blue, indigo, and violet are the main ones that are in that spectrum. And how plants actually capture the light is the same way that we do. They're going to use pigments, which are molecules that are going to absorb that light. And these pigments are actually going to absorb different parts of the light, because there's no pigment that is going to be able to absorb there's no pigment that can absorb all of the visible light spectrum. So for example, in humans, we are able to absorb sections of red, blue, and green, because we've got red, blue, and green cones in our eyes. Plants, they have pigments that can only absorb specific wavelengths of energy out of the visible spectrum. Since their pigments can only get certain sections of it, they actually produce several different types of pigments. So the one that I've mentioned already is chlorophyll, and they actually produce more than one kind of chlorophyll. So chlorophyll A, that's their primary pigment. So this is the main pigment that plants are going to make, and they're going to have a majority of their pigment as chlorophyll A, but they're also going to make chlorophyll B, hence the A, and they're also going to make a group of pigments called the carotenoids, and we'll find out here in a little bit why they're called carotenoids. So what we're going to do next is I'm going to show you a graph that has the three different groups, so chlorophyll A, chlorophyll B, and the carotenoids graphed out, along with which sections of the visible spectrum they can absorb. All right? So we can see why they need all three of them. So here's the graph, and you can see the three different ones. So chlorophyll A is this dark green line, chlorophyll B is the light green line, and the carotenoids is the orange line. Okay? So we're going to take them one at a time and take a look at them. So you can see the spectrum, the electromagnetic spectrum for the visible section, and we go from violet to red. And the way that this graph works is the energy absorption increases on the y-axis. So anytime that there is an increase in the line, so any place there's a peak, or actually any place where it's above right here, so any place there's an increase, that means that that pigment can absorb that color. Okay? So, for example, chlorophyll A, this dark green one, has an increase right here, right? It's pretty high, so it can absorb purple. It can also absorb blue, right? The purple indigo blue section, because it's got another peak right here. And then if we go across, we also see that chlorophyll A can absorb orange and a teeny bit of red, but it's mainly orange. So chlorophyll A can absorb, let me grab my pen. So this one can do purple, indigo, blue, and orange. Guess I should make that violet, right? Make that a V. Okay. So what I want you to do now is take a look at chlorophyll B. What colors of the electromagnetic spectrum for the visible spectrum can chlorophyll B absorb? So taking a look at this light green line, which colors can chlorophyll B absorb? And my guess is you may have said violet, but you definitely would have said blue, right? And indigo. So indigo and blue. So maybe violet, indigo, blue. Pretty much cuts off there, right? And then if we come across, it can do yellow and orange, right? And I guess, yeah, we could put over on this one chlorophyll A some red, right? So then what about the carotenoids? Well, the carotenoids, they can absorb violet, indigo, blue, and some of the green, right? What color can none of the pigments really absorb well or at all? Yeah, you should notice that they are not able to absorb right in here, which is mainly green. The carotenoids can absorb just a scotch of the green, but mostly we're in that green section, right? That is actually really important. We'll get to that here in a second, okay? So you can see why these plants need these different pigments, right? Because they can absorb different ones, but some of them are much better at absorbing, right? So like chlorophyll B, it can absorb yellow, and it can absorb some of these orange sections to kind of overlap with chlorophyll A, right? And the carotenoids can absorb sections that neither of the pigments of chlorophyll can. So let's see what this means as far as things like the colors of plants, right? So why is it so important that they can't absorb that middle section, that greenish yellow section? Well, here's why. So you've got the light coming in, and you can see there's the spectrum that we were just looking at of what they can absorb. If you can't absorb a color of light, that means you reflect it, right? And so this section right here is green with a little bit of yellow. Well, that's why almost all of the plants are going to appear green to us, because that's the color of light that they can't absorb and they reflect, right? So I don't know if you can see my shirt, but or tell what color it is. My shirt is blue, and that is because it appears blue because my shirt is absorbing all of the different colors of light except for blue. And so it's reflecting the blue light back at the camera. Okay? So during spring and summer, that's what those pigments are going to be doing. It's going to be absorbing everything except for that green and a little bit of yellow that the pigments can't absorb, because it's got chlorophyll A, chlorophyll B, and the carotenoids. But come fall, what happens to the leaves? Right? They change color. And the reason why they change color is because chlorophyll A and chlorophyll B, the molecules get broken down out of the leaves and pulled into the tree or the plant and stored, right? Because these are expensive molecules, so they don't want to throw them away. So they're going to store those molecules, but they don't have very many of the carotenoids out there. So they're going to bring in chlorophyll A and chlorophyll B, which means there aren't a lot of them out there anymore. And it's mainly the carotenoids that are going to be left in the leaves. And if we go back and look, if you take a look, what is it that the carotenoids can't absorb? They can't absorb these colors right here, right? They can't really absorb much of the green, but mainly they're not absorbing yellow, orange, red, okay? And that's why they're called carotenoids, because what color are carrots? Orange, right? And so this is why leaves in the fall start to appear red and orange and yellow, because these carotenoids are in those leaves, but the chlorophyll A and chlorophyll B are not. All right. So that wraps up light. The next lecture is going to be on the details of photosynthesis.